Here is a claim to hold onto for the whole episode. An attention head is a learned content-addressable lookup. At one position, the model forms a query, a description of what it is looking for. Every position advertises a key, a description of what it holds. The query is compared against all of the keys, a softmax spikes on the closest match, and the head returns that position's value. Read it as a pointer dereference. The query says, I want the thing at the position that looks like this. The keys say what each position is. The softmax finds the one that matches, and out comes its value.
Is that not just a fancy weighted average? Attention pays a little to everything and mostly to whatever is nearby.
That is exactly the picture to unlearn. The earlier architectures did commit to nearness. A convolution bets on nearby pixels, recurrence bets on recent time steps. Nearness was hardwired. Attention makes no such bet. Which positions matter is not fixed in advance. It is computed from the content. Position by position, on the fly. Nearby and relevant are allowed to be completely different things, and attention can tell them apart. So the whole structural prior of a transformer is this one move. Not locality, not recurrence, but a learned mechanism for deciding which positions matter. Sit with how different that is. A convolution comes with its answer already wired in. Relevance means nearby, full stop. Recurrence wires in. Relevance means recent. Attention refuses to name relevance up front. It ships a mechanism for discovering relevance and lets the data fill it in. The bias is not a fixed answer. The bias is the shape of the question. If you followed the next token prediction series, you met attention there from the sequence side. Here we read the same mechanism as an assumption about the world and grade it like every other architecture in this series. Here is the mechanism, stripped to 3 lines of real code from the from-scratch transformer. First, the query is matched against every key. Take the symbol Q, and for each position dot it with that position's key. The dot product is large when the two point the same way, so that one number scores how well the query and that key agree. Second, a softmax over those scores turns them into weights that sum to 1, sharp when a single key clearly wins, flat when nothing stands out. Third, those weights multiply the values and add them up, so each position contributes in proportion to how well it matched. When the softmax is sharp, that weighted sum is almost entirely one position's value. The soft lookup has become a hard one, a pointer dereferenced. And notice, Q, the keys, and the values are all just learned projections of the input. The model decides, by training, what to look for and what to advertise.
But that only works if the useful position actually looks like the query. What if it does not?
That is exactly the right worry, and it names the assumption out loud. Content-based addressing bets that relevance is computable from similarity. In the learned space, it bets the model can encode the keys so that the positions worth reading are the ones whose keys resemble the query. When the task structure can be written that way, attention finds it every time. It is a very general bet, which is why one mechanism serves translation and code and protein folding. But it is still a bet. When relevance has nothing to do with any similarity the model can represent, the mechanism has nothing to grip, and no amount of training will conjure the grip from nowhere. The prior has to actually match the problem, the same lesson as every episode before this one. A claim about a mechanism is worth more if you can build a task that demands it. So here is a deliberately tiny one. Feed the model a string of memory bits, then an address, and ask it to output the memory bit at that address. To get it right, the model has to read the address and fetch the bit it points to. That is content-addressable memory, stripped to the bone. And notice what cannot solve it. A fixed window of recent bits cannot, because the answer lives wherever the pointer happens to land, near or far, and no fixed offset from the end reaches a moving target. The convolution's locality bet is no help here. The recurrence's recency bet is no help either. A model with no lookup mechanism cannot do better than guessing. That is the whole point of the task. It is a clean instrument that only a lookup can pass.
And a transformer just learns this on its own from examples.
It does, and the satisfying part is that you can watch it happen. At the output position, the relevant head puts almost all of its weight on the addressed memory cell. Not spread across the neighbors, not hedged, concentrated on the one cell the address points to. The pointer dereference is not a metaphor you are imposing from outside. It is right there in the attention weights, plainly visible. The mechanism we argued for on paper is the mechanism the model actually found without ever being told to. Hold onto how clean this looks, because in a moment it is going to get complicated. Now, one attention layer is not enough, and the reason is structural, not a matter of capacity. The query at the final position is built only from that position's own token, so it does not yet know the full address, because the address bits live at other positions, spread out along the sequence. It cannot route to a cell whose identity depends on bits it has not seen. You cannot dereference a pointer you have not finished reading. And this is not something you fix with a bigger layer. A wider single layer still forms its query from one token. It has more room, but the same blind spot. One lookup is simply not enough lookups.
So how does adding a second layer help?
The first layer does one job: gather the scattered address bits into a single place. The second layer takes that assembled address and does the actual fetch. Two lookups composed one after the other, and that is the general picture. Transformer depth is, quite literally, how many lookups you can chain. Each layer is one more stage of dynamic routing. Then a clean experiment earns its keep. Scale the memory up, and the two-layer model stops solving the task. Here is the part worth sitting with. Making it wider does not help. Training it longer does not help. It sits at chance plus a little, no matter what you throw at it. Add one layer, holding the width and the training budget fixed, and it flips from stuck to solved. Depth is the knob, width is not. A larger memory needs a sharper, more assembled query than two layers can build, and the third layer is where that extra assembly happens. How the gradients that train those layers actually flow is its own from-scratch series, coming later. So what does this bias cost? Every architecture buys sample efficiency with an assumption and pays a bill when the assumption bites. Attention's bill has two lines. The first is compute. Comparing every query against every key is quadratic in the length of the sequence. Double the sequence, and you quadruple the work. That is the price of letting any position reach any other, and it is why long context is expensive. The second is order. Because the mechanism is pure content matching, it has no built-in notion of position. Shuffle the inputs, and a bare attention head cannot tell the difference. To it, a sentence is just a bag of tokens. Order is real information, so it has to be added back in, by hand, as a position encoding. The convolution and the recurrence got order for free from their structure. Attention gave that up to buy reach. Which lets us fill in this episode's scorecard, the same 3 rows we grade every architecture on. The bias, relevance is computable from content. The win, any position can reach any other, on the fly, decided from the data. The bill, quadratic cost, an order that is not built in. That is the whole trade attention makes, laid out in 3 lines.
On the memory task, we could see the lookup right there in the weights, so the weights explain the model.
On that tiny task, with 2 layers, yes, the attention plainly showed the dereference. But watch the step you just took. You slid from the weights, are high to the weights explain the computation. Once the task gets hard and the model gets deep, those 2 things come apart. Whether a high attention weight really means a token mattered is exactly where the next episode picks up.